I'm going to solve the fourth partial exam of electricity and magnetism. The first problem says like this. The current density in a cylindrical conductor of radius capital R, that is this one, varies as J for small r equal to J naught times R over capital R in the region from 0 to capital R. Express the magnitude of the magnetic field in the regions from small r to capital R and from R bigger than capital R, and produce a sketch of the radial dependence for the magnetic field. For determining the magnetic field, we have to use Ampere's law that says that the integral of the magnetic field times the derivative of the differential of the area here, it can be the differential of the area. It's equal to mu naught times the enclosed current. But we also know that the enclosed current, it's equal to the integral of the current density times the differential of the area. So we can substitute here that density current for the given one. So we use J naught times small r over capital R, and this times our differential of our area. The area of this cylindrical part, it's only 2 times pi times our radius, and this over v times dr. Okay, once we have this established this current, we have to determine that will be all that the r small r has to be smaller than capital R. So we are only considering until this part. So we are integrating from 0 to small r. So once we integrate all this part, we will obtain here that the integral is equal to 2 pi, that is this part, times our J naught over R, that is this part, times our radius 2 times, but we are integrating, so it's elevated to the cube over 3, and we evaluate it from 0 to R because of this part. As we are evaluating it in R, we are leaving this exactly the same. So this is equal to 2 times pi J naught, like this, over 3 times R, like this, and our R cube in here. So once we have the current, we can write here that our magnetic field will be equal to this part. We have to move it here dividing, so the magnetic field will be equal to mu naught, that is this, times our current enclosed, that is 2 pi J naught R cube over 3R, but we are dividing it by dA, and dA is going to be 2 pi R, also because it's the same one as in this part in here. So once we divide it in here, the 2 pi R cancel, and we cancel here the cube and put it only square. So this is the answer for the first part, but we are told to obtain then that the small r has to be bigger than the capital R. So for obtaining that part, we do exactly the same part as in here for the current. So the current enclosed will be equal to 2 pi j naught over our radius times r3 over 3, that this part is exactly the same one as in here, but we are evaluating here from 0 to capital R because now the capital R is bigger. So now we are considering this part until here. Okay? So as we are considering from 0 to capital R, we are evaluating differently, so we are left with 2 pi j naught over R, but then here this R turns into capital R cube over 3. And then once we move this part dividing, we can cancel the 2 pi, but the radius is not cancelled. So we are left with B equal to mu naught times J times R squared, because we cancelled this one with these 3 and we are left only with 2 here. And we are left here with the 3 and our R with our radius from this part. So this is the second magnetic field that is asked in here. And once we graph it, I'm gonna graph it here. Here we will have our magnetic field, and here we will have our radius, and here we will have our capital R. But here we have the cylindrical part itself. Once the radius is approaching to the cylinder, to the magnetic field, it will be rising. But once the radius is decreasing, the magnetic field also will decrease. So this is how the sketch will look, and this is how you solve this problem.